All right, extraction and use of metals. By the word extraction, it means that we are going to take that metal out of the Earth's crust. Now, we use the word extraction because metals are usually not present in their purified forms. So we take them out, we purify them, and we convert them into pure metals. The whole process is commonly known as extraction. Once we're done converting them into pure metals, next step would be using them to our own advantage. And that's where the use of metals of this portion lies. Now, moving on with this chapter, extracting metals, the common words that we use from their ores. Now, what is an ore? In order to define it, we have some words to clarify. Starting off with minerals, most metals in the earth crust are combined with other elements. Mostly that's going to be oxygen, which means most of the metals are present in the form of their oxides. Those individual compounds are known as minerals, right? For example, iron is found in the form of either pyrite, which is iron sulfide, or magnetite, which is iron oxide. Now, you can see both the ores and you can see how different colors they have. That's usually because ores tend to have different compounds attached to them. From what's given over here, on top of this, they would have other compounds attached to them. Apart from other compounds, we have some earthy particles, we have soil attached to it, sand attached to it, silt, small pieces of stone, gravel, the list goes on. All right. So definitely there are unwanted materials over there. Sometimes there are other minerals combined with them. Now, ore is actually a sample of rock that contains enough of the mineral to be worthwhile to extract the metal, which means ore would be enough quantity of that metal in the form of a mineral to be extracted, and it's actually worth the while, it's actually worth the price. Now, the price of the metal is affected by how common the ore is and how difficult it is to extract the metal from the ore. So that's how it works. All
Mm.
right. But most of the metals are usually taken out of Earth's crust. A very few unreactive metals, such as uh, we can also add to the list copper, we can add to the list silver, gold is a part of the list, platinum is also a part of the list. They're usually found native. Native means that they exist naturally as an uncombined element, which means gold with the symbol AU exists as AU, not an oxide, not a chloride, not a sulfide, the gold itself. Silver and copper are also sometimes found native, although much more rarely, which means
So,
copper would be found in other forms as well.
so sir,
You
it
were,
means that elements such as gold they are found without like unwanted materials.
yeah, and there is a reason behind that. Don't forget that in the previous chapter, we studied the reactivity series. And if I take you back to the reactivity series, no, that's not the complete reactivity series. Let's go to the one that is complete and that has all the metals that we have studied on it. Now, take a look at this. Now, gold is present at the very bottom of the list, which means it's the least reactive one. That's why it's found native. It does not react with anything. It's not going to react with oxygen in the air. It's not going to react with other gases in the air. It's not going to react with water or other materials around it. So, yeah, it's easy. They can be
Alright.
found native. So does silver, so does copper. So sometimes, I mean, rarely would be a much better adjective to use over here. Rarely, copper and silver are found in their native states, mostly gold, or I added to the list platinum at the bottom of the list. Platinum is commonly named as white gold. So, yeah, we find those in native states. And the reason behind it is their least reactivity. Okay, so
Yeah.
getting back to where we were, my bad, this was the page. Okay, so uh, an important hint, you do not need to remember the names of ores, minerals, or their formula, which means pyrite, iron pyrite, Fe2, magnetite, Fe3O4. You don't need to go with that. They won't be asked in exam. And that's actually a good thing. because there are so many ores and so many minerals. You can't just keep memorizing them all, and there is no need to. Moving on to the next part, extracting the metal. Now, many ores contain either oxides or compounds. Usually, by compounds, most of them are going to be sulfides. So they can easily be converted into oxides. For example, sulfides such as sapphirite, zinc blende, which the common name, ZNS, zinc and sulfur combined, can easily be converted into an oxide by heating in air. Why? It's going to react with oxygen. It's going to form an oxide and sulfur dioxide. So both of them oxidize. Remember, when zinc is oxidized, it gives us ZNO. When sulfur is oxidized, it gives us SO2. In this case, both of these elements actually are oxidized and oxygen added to them. All right.
Yeah.
However, if we look closely at it, you will see that zinc does not change its state. That's a common term that we use there, oxidized, but zinc will move from +2 to +2, so no change in zinc. Sulfur is -2 minus over here. Sulfur becomes 4 plus 4 over here. Oxygen is -2 over here. Oxygen is -2 over here. However, oxygen is 0 over here. Which means if I talk about the redox reaction terms, sulfur is the one that is oxidized and oxygen is the one that is reduced. Okay? I'll practice this kind of stuff with many questions upcoming in the book. This would keep you on top of your toes for the oxidation reduction stuff.
All
All
right.
right.
Yeah.
So, yeah, not to forget, this process is known as roasting. So, whenever you see the word roasting, it means we took a compound and we heated it in air so much so that it changed its identity and formed something new, probably oxide. Okay.
Yeah.
So, again, if you have forgotten about oxidation induction, you might find it useful. Read chapter number 14, you'll have the idea. To obtain the metal from the oxide, you have to remove the oxygen. Removal of oxygen is called reduction. Metal exists as positive ion there in their ionic compound. And to produce the metal, you have to add electrons, which means addition of electron is known as reduction. And in order to extract the metal, we will reduce the oxide. All right. Now, how
Yeah.
much is a metal extracted depends upon, to a large extent, of its position in the reactivity series. Now, we're going to divide the whole reactivity series into different parts to understand which processes we usually go with. Now, a manufacturer obviously wants the cheapest possible method of extracting an iron from an ore, extracting a metal from its ore. The two main economic factors that we take into account is the cost of energy and the cost of producing agent, right? You'll
Yeah.
understand these points as soon as we go with an example. Because if I don't quote an example, the cost of energy and the cost of producing agent will not make any sense to you. So let's move ahead, keep on reading, since an example would clarify it much better. So I'm going to come back to this part once I've given you an example. So moving on, metals below carbon in the reactivity series. Now remember, carbon is the only non-metal on this list, not the reactivity series. On this list, carbon is the only non-metal. Now there are some elements, some metals on top of carbon. Definitely they are more reactive than carbon. There are some that are present at the bottom of carbon, zinc, iron, copper, etc. They're definitely less reactive than carbon. Now, for a metal below carbon in the reactivity series, the cheapest method would be to reduce the ore is to often heat it with carbon. Now, carbon is present in Earth in abundance, in a very good abundance. That's why carbon is actually very, very inexpensive when it comes to that. So, if I quote this example, I literally give you the idea of the cost of the reducing agent. Make sense?
No
The
sense.
reducing agent is carbon, and carbon is really inexpensive or cheap because it's available all around the planet in the form of fossil fuels, mainly coal, or you may also find it a part of some liquid fuels, gaseous fuels. Any fuel you name, carbon is definitely a part of it. Fossil fuel I'm talking about, right? So
Yeah.
it gives you an idea, but the example is not complete yet. Let's keep on moving. The extraction of iron is a very good example of this. What do? We have an iron ore present in this form. It is iron 3 oxide, which clearly tells us that the state of iron in this one is plus 3. Now, how do we extract that iron? We heat it with carbon. This is the reaction with carbon. We either get this iron and we get this carbon monoxide. Now, why would this reaction proceed? It's pretty easy. Carbon is higher in the reactivity series. I'm going to move back a little bit. See, carbon is up top, iron is below, which means carbon is more reactive, iron is less reactive. If I go back, you'd notice you'd notice that carbon can displace iron, form its oxide, and put iron apart. So of course, carbon will take away the oxygen from the iron oxide. This is a redox reaction. Iron trioxide is reduced to iron. Carbon is oxidized to carbon monoxide. So the reducing agent, this definitely becomes the reducing agent. This is Ra. This is oxidizing agent OA. So that's our reducing agent right there. Makes sense? And this
Yeah.
is a displacement reaction. Why? Because carbon is more reactive than iron. It can easily displace it. Now, the only thing that might be bugging you in this whole scenario is that this one's a solid, this one's a solid. We understand carbon monoxide is a gas, but why is this one a liquid? Iron is usually present in the form of a solid at room temperature. Any piece of iron or iron metal used anywhere around you right now, the room you're sitting in, is probably in solid state. How come iron is liquid over here? We're going to explain it ahead. So extraction of iron is carried out in a, a whole big equipment or industry. This whole is known as blast furnace. It can be as small as a simple equipment, or it can be as big as an entire industry of extraction of iron. The process is a bit more complicated than what we have shown over here, but this is more like a simplified form for students. Other reactions also occur, but the main reducing agent is actually carbon monoxide. So actually, instead of this reaction happening, this reaction happens in the blast furnace. Our
Uh-huh.
oxidizing agent is iron 3 oxide again, but this time we have a little bit different of a reducing agent. That is carbon monoxide is our reducing agent. So our products are iron and carbon dioxide. Now, let's understand how that goes in the actual industry. This would give you a very good idea. Now, let's go through this diagram a little bit for just for the understanding. Although the hint is mentioning over here that you are not required to learn the details of a blast furnace, but just to give you a better idea. So we have iron ore and we have coke, which is carbon, and we throw in some limestone. This is just to really cater the impurities. And we throw them from up top. Notice that the temperature on top is 400 degrees centigrade and temperature at bottom where we are burning everything up is around 1800 degrees centigrade. And we have blasts of hot air coming in, hence the name blast furnace. Furnace means where you burn something. Blast means thrusts of air. So the thrusts of air are coming in from the bottom and going out from the top. We get molten iron over here and we get some waste which we call slag, molten slag over here. They form two different layers because they have different densities and they are not soluble into one another. All right. This
Mhm.
is just to give you an idea. Now, this is where the whole burning occurs, and this is where the iron ore, which we have been calling Fe2O3 in the solid form, is reacting with three molecules of carbon monoxide, which is a gas, which produces for us iron, pure iron, as actually a liquid, and it also gives us three molecules of carbon dioxide as a gas. Now, carbon dioxide is leaving the system, hence this hot phase gases. 1800 degrees centigrade. I'm only going through with this diagram just to explain you these basics so that you don't have a problem. Now, 1800 degrees centigrade is good enough of a temperature to melt iron. Hence, the iron is written as a liquid. I hope this clarifies it. We do not need to go with the further details of the diagram since they are not required in Edexcel. Although we read a very good details as a part of Cambridge, but Edexcel, keeping it easy, does not require you to read the details. That's about it. Now, this gives you a really good idea of 2 points, the cost of reducing agent and the cost of energy. A reducing agent is actually giving out the energy because it's burning. Carbon can burn as coke, so it would produce the energy and it would also act as a reducing agent. So, keeping these two in mind, the manufacturer is actually using the cheapest possible way. And remember, this method was anything that was below carbon. So, what exactly do we do for something that is above carbon on the list? That still poses a question, right? Because yeah, iron is below carbon, we can go by this method. Zinc is below carbon, we can go by this method. But carbon will not be able to displace any of these. Why? Because they're all more reactive than carbon. So this method definitely cannot be used for aluminum, magnesium, calcium, or whatever's on the list up top of carbon, right? So
Yeah.
in order to answer that question, let's go back to the next topic. And this topic actually caters it metals above carbon in the reactivity series. Now, ores of metals higher in the reactivity series than zinc can't be reduced using carbon. Why? They're more reactive than carbon. Even at reasonable temperatures, you won't be able to do it. So, metals are more reactive than carbon. Carbon will not be able to take oxygen out of the metal oxide. So, metals above zinc are usually produced by electrolysis. Now, this is why we need to understand electrolysis separately, because this chapter uses electrolysis as a part of it. Okay, so I'm going to just skip this portion for now, since we're not done with electrolysis, and I'm going to move to alloys. We are just skipping half a page, all right? We'll do it as
Yeah.
soon as we are done with electrolysis, both
All right.
this portion as well as the key point, right? So moving on to alloys. Now we already know alloy is a mixture of metals mostly. Sometimes we add uh, carbon or other non-metals to it. How do we do it? We simply melt the metals, mix them well. We let them solidify again at room temperature. There you go. You have formed an alloy. For example, brass is a very famous alloy. It's actually a mixture of copper and zinc. Steel is a very famous alloy. It's a mixture of iron and carbon. Sometimes other metals are also added. So the point is, why are we making alloys? First reason, alloys are harder than individual pure metals. Now, this needs to be explained. Why are alloys harder? Now, if you remember metallic bonding, this diagram must be easy for you to understand.
Slide
Metals,
over.
yeah, metals exist as cations, and the electrons are present in between the layers as delocalized electrons, right? And
Uh-huh.
metal ions could slide over one another, which actually gave metals the ductility to be able to convert it into wires or malleability to be able to be hammered into sheets. Now, alloys are harder. Why? Because we use different metals. Now, this one is definitely a different metal. This one is definitely a different metal. That's why their sizes are different. When the sizes are different, two different sized atoms are put together, they break up the regular lattice arrangement, which makes it more difficult for the layers to slide over one another. Hence, alloys become harder. Now, I tell my students that alloys become hard by compromising their properties. Of course, if they're going to hard and they won't easily slide over one another and it would be become a difficulty, of course, that means their malleability or their ductility has been compromised slightly. Remember, you can give them a new property such as more hardness by compromising a previous property. Although the questions related to compromise are usually not asked in Edexcel. Make sense?
Yeah.
So remember, a metal consists of a regular lattice of the metal ions, positive ions to be exact, surrounded by a field of delocalized electrons, as I just said. Some common alloys include bronze. Now, as soon as we say the word bronze, some sports come into mind, the common medals come into mind that we commonly use for our sports around the planet. For gold medal, then there is a silver medal, then there is a bronze medal. Bronze is actually made of copper and tin. Then there is stainless steel, the spoons and forks we commonly use, which is an alloy of iron with chromium and some amount of nickel. A mixture of copper and nickel is commonly known as cupronickel, which is used to make silver coins. Cupronickel looks like silver, it isn't silver. There are many alloys which give us a different appearance. Maybe they have a different appearance, maybe more hardness, maybe some other different properties. So let's go with some properties and uses of some metals to have a better idea. Now, uses of aluminum. Pure aluminum isn't very strong. So what do? We make aluminum alloys. Aluminum can be strengthened by adding other elements. If we can add silicon, if we can add copper, if we can add magnesium, we can definitely increase the strength of aluminum. Aluminum can resist corrosion. It has a low density. It is a good conductor of electricity. One thing that it lacks is strength. So sometimes the aluminum in the cables in the photo is also strengthened by a core of steel. Core of steel means we use inner part as steel and we wrap it around by AL. This small portion is AL, this small portion is AL. So steel is strong. If aluminum is wrapped around steel like this, or maybe just on top of it as layers, it can work well. It will have strength and it would have all of its properties as such. So we also use aluminum to make planes, electricity cables, pots, and pans. The pans we commonly use for frying at home. It is low density, it has a great strength when alloyed, its ability to conduct electricity and heat is put to a very good use, and it can also resist corrosion. It does not get corroded, it does not turn into small flakes and fall off. That's the best part of aluminum. Aluminum, however, resists corrosion because it is very thin but very
Uh-huh.
strong, and it forms a layer of aluminum oxide, which is Al2O3. Now, the best part about aluminum is that if you have a piece of aluminum, the topmost layer will get corroded and will be converted into Al2O3. The bottom layer is still Al, but since this layer is non-porous, this layer acts like a block, so it prevents anything else reaching the surface and reacting with it. So this AL will never react with water, will never react with air, and will never get corroded. Unlike iron, if we have a piece of iron, the topmost layer is going to be converted into Fe2O3. Now the problem with Fe2O3 that it is going to fall off in the form of small pieces. We call these pieces as flakes. I hope you're familiar with the word cornflakes, the common breakfast what they
Uh-huh.
are used for, the breakfast meals. Now, those flakes are pretty simple and small, and from the word flakes, you get an idea of what happens to iron after it gets corroded. But the same does not happen to aluminum oxide. So, this difference keeps aluminum intact and resistant to corrosion as opposite to iron. So, that actually makes aluminum very, very useful. Iron, because it can corrode, so we try to convert iron into steel. How do we do that? We add various proportions of carbon and other metals. For example, Iron and carbon mixture is commonly known as steel. One of the kinds of steel is mild steel. Now, mild steel is an alloy of iron which consists about 0.25% of carbon. Now, that's a really small percentage. Now, the small amount of carbon increases the hardness and the strength. Mild steel is a strong material. It can be hammered into various shapes. It's malleable, still malleable. It's still ductile. It can form nails, car bodies, shipbuilding, girders, bridges. A lot can be done with mild steel. A disadvantage of mild steel is that it rusts when exposed to oxygen and water. It is about 3 times denser than aluminum, which means heavier than aluminum, of course. Some car bodies are made from aluminum. A car body will not rust if it is made out of aluminum, and it would be lighter. Less fuel has to be used. Previously, we were making cars out of mild steel. The cars were heavy and they required more fuel. They also got rusted if they were washed over and over again and not dried in time. But now we are making cars out of aluminum. They don't get rusted. They are lighter, and since they are lighter, they use less fuel. That makes much sense, right? Does it?
Yeah.
Great. Now, remember a very important point. Sometimes the car body, which is made out of mild steel, is painted. The paint is mainly for decoration, but it is not used to prevent rusting in case of aluminum. But the paint initially for mild steel was to prevent rusting. We started painting cars because we wanted to keep them safe from rusting because they were made out of mild steel. Later on, we started making it out of aluminum, but we were still painting them for decoration because that's how we like our cars decorated, good looking. Cars are a sensation, so yeah, the decoration is very important when it comes to cars. Okay, so moving on to another category of steel, high carbon steel. The name itself suggests that we are going to use a higher percentage of carbon. Take a look, 0.6 to 1.2%. And we were just discussing about 0.25% for mild steel. So, of course, this percentage is much greater. It's anywhere from double to 5 times of the percentage, right? So, these amounts are variable. High carbon steel is harder, more resistant to wear. It's more brittle, means it's not as malleable or ductile. We can't give it too many shapes. It is mainly used for cutting tools. High carbon steel is usually converted into different kinds of cutting tools. Now, I hope you're familiar with most of the knives, if not with this. Now, they also contain some small amounts of manganese. Moving on, stainless steel, as the name suggests, stainless means it will never get stains on it. What kind of stains? Rust stains. How? We add some chromium. We add some nickel too. Now, chromium is just like aluminum. It forms a strong oxide layer in the same way as aluminum. This layer protects the iron as well. So, adding some chromium actually allows iron to be resistant to corrosion. That's a great way to do it. Now, we make kitchen sinks out of it. Kitchen sinks shine all the time. If it gets dirty, wash it, it shines again. Saucepans, knives, forks, no matter what food you have eaten with your knife and fork, wash it, it will become good as new, right? We commonly use forks to eat meat and we use many dips. Ketchup is right there. Ketchup is very bright red, but of course, once we wipe out the ketchup out of that fork and we wash it, it would be good as new. Gardening tools, there are many major uses. The major uses also include it in brewing industry, the dairy industry, milk and cheese production, chemical industries. Wherever corrosion-resistant vessel is required, stainless steel would be used over there. Stainless steel is very expensive than mild steel, significantly more expensive. But of course, the use requires something that never gets rusted. Why? Because rust is not good for human health. Human bodies cannot process rust. So we need something that would never get rusted. Hence knife, forks, because we're going to use it for eatables, so it should never get rusted. So this table actually gives you a very good comparison of mild steel, high carbon steel, stainless steel, what are we using in it, and what other uses after the production of alloy is done. Now these are mostly facts. Moving on, the last portion, copper. Copper can be used in electrical wires. Why? It's a very good conductor of electricity and it's ductile. Copper can be used in pots and pans like shown in the diagram. Why? Because it's a very good conductor of heat, unreactive, does not react with any of our food, no matter how acidic or alkaline our food is, what kind of food that is, whether it's going to be strong, reactive, or non reactive, it won't react. And it's very malleable, which means we can easily convert it into pans. Copper was also used for water pipes. Why? It was unreactive. Whether we are using cold water or hot water, it never reacted. So it is also malleable, so it's easy for us to convert it into pipes. Lastly, surfaces in hospitals. The usually surfaces in hospitals, especially the working area, we use copper because it has antimicrobial properties. Since copper is not reactive, so microbes cannot actually stay alive for a longer duration on copper, which is good as well as for pots and pans, as well as surfaces in hospitals. Since it's malleable, so we can easily convert it into big sheets for big working spaces in hospitals. There you go. That finishes the